In class, we talked about the test for divergence, or the divergence test, and we talked about the logic behind how you would use it. And we realized that if a sub n goes to 0, then we still don't know whether or not the series converges or diverges. So we need additional tests. And the first test we're going to talk about in this series of videos is called the integral test. It turns out that whether or not an improper integral converges or diverges relates to whether or not a series converges. So we're going to talk about this through an example, which is a pretty famous series that has its own name called the harmonic series. It's the sum from k equals 1 to infinity of 1 over k. In other words, it's numbers of the form 1 plus 1/2 plus 1/3 plus 1/4, etc., going on forever. It's the sum of the reciprocals of all the positive integers. Now, when you calculate the partial sums, you get this data. So we have the first 9 partial sums of the series. There's nothing here that tells us whether or not it converges or diverges. I mean, we do notice, like we did with the series 1 over k squared that we talked about in class, we do notice that the space between consecutive partial sums seems to get smaller, which is an observation we had with 1 over k squared series. But that's not enough to tell us what is going on. If we even went up to n equals 1,000, we would get 7 point something, which is still kind of a low number. So we don't really know either way what's going on. That's why we need what's called the integral test. But before giving away what that test is, we want to explore the concepts behind this thing called the integral test that's going to be very useful to us. So we're going to do that through this activity. We're going to consider the harmonic series, summation from k equals 1 to infinity of 1 over k. And we're going to remember that this series will converge if the sequence of partial sums converges. This is the compact form of what the nth partial sum will look like. This is the expanded form. Notice how we can rewrite that partial sum. We can write it as 1 times each number in that sum. Now, why would we want to do that? Well, we can think of the partial sum the way we originally wrote it. We could think of it as lengths of line segments. So this line segment we could think of as length 1. This could be length 1/2. This could be length 1/3. This could be length 1/4. This could be length 1/5, etc. Okay, so if we do that, then that's length. But if we multiply everything by 1, it doesn't change the value numerically, but we can now interpret each of these terms as if it were an area of a rectangle rather than the length of a line segment. So when we think of this partial sum as areas of rectangles, then we're thinking of the base of each of these rectangles as being 1. Now I know my picture is not to scale because I have length 1 here and length 1 here. That doesn't match. But the point is that I can think of each of the terms in the partial sum as the area of a rectangle with base 1. All of these rectangles have base 1, which means I can interpret the nth partial sum as a series of, I used the word series. I gotta be careful with that. Let me use a different word. I can think of the terms of this partial sum as a collection, let's use that word, of rectangles. The areas of those rectangles added together, basically. Okay? So we have these green rectangles here, and the sum of the areas of these rectangles is equal to the partial sum. If we were to add all these numbers together, we would get the sum of these areas. I know we don't go up to n, we don't know what n is. This is just a picture of however many we can fit here. But hopefully that analogy makes sense, that we're thinking of each term as the area of a rectangle. And we make the observation that the heights of these rectangles are all the function values of this function for different positive integers. Now notice we don't just have rectangles in this image, we also have a curve. And this curve is the curve y equals 1 over x. Notice the connection between 1 over x and 1 over k. This is the continuous version of 1 over k. And so then it's not a coincidence that this curve is passing through vertices of these rectangles. So now we have to remind ourselves, what does the integral mean? When we first learned the integral, what is the integral? The integral is the area under the curve. So what I'm shading in yellow here is what would be the integral of this function. So integral of 1 over x dx from 1 to, I'm not sure yet. We'll talk about that in a moment. It's really important to understand this pictorial connection between the partial sum, which will eventually refer to the series, the infinite series, and the integral, the related integral. So with this setup in mind, you're going to work on activity 8.3.5. So you should have already tried this as I instructed on Canvas before watching these videos. You'll get more out of it if you try the problems first and struggle with them, and then watch me explain how to do them here. So if you haven't had a chance to do that, go ahead and pause the video and try these questions based on what we discussed regarding the setup here. Okay, so we kind of answered A just now by with what we were annotating in the picture here. And we answered B over here, except we left this as a question mark. So to fully answer part B, we noticed that the integral would go from 1 to 10. So I would write a 10 there for part B. To answer which is larger, the definite integral or the ninth partial sum, which would be the sum of the areas of these rectangles, which would be bigger, which would be larger, well, we can see that the partial sums kind of stick out from what the integral would be, which means this the partial sum would actually be larger. If we generalize this in part D by considering the nth partial sum, which is all of this, and we let n go to infinity, that's the same as letting the upper limit of this integral go off to infinity. In other words, it's this definite, or this improper integral here. The question is, which of these would be larger and why? Now notice that this pattern of having the rectangle stick out above the function above the curve, is going to be consistent throughout. Yes, it gets smaller and smaller, that difference between the rectangle and the area under the curve, but that pattern is consistent throughout. So it turns out that the series will be larger than this integral. So then the question is, does the improper integral from 1 to infinity of 1 over x dx converge or diverge? Let's work out that integral right now. Just as a little review of improper integrals. So we have integral from 1 to infinity of 1 over x dx. What do? We set it up as a limit as b goes to infinity of integral from 1 to b of 1 over x dx. The antiderivative of 1 over x is ln of absolute value of x. But since our interval only involves positive numbers, I'm just going to do ln of x just to keep it simple. Evaluated from 1 to b. Now, you should notice I just made a mistake. I omitted something. I left something out. We're supposed to be taking the limit here. So I should write that in. Limit as b goes to infinity of ln of x evaluated from 1 to b. All right, so we have limit as b goes to infinity of ln b minus ln 1. We should remember that ln of 1 is equal to 0, so I can cross out that ln of 1 because subtracting 0 doesn't change anything. And then I have limit as b approaches infinity of ln b. So if you're not sure about that limit, you should remind yourself that when we learned about the graph of natural log, it actually goes off to infinity. It goes very, very slowly to infinity, but it goes off to infinity. The y value goes off to infinity as the x value goes to infinity. So the answer to this integral is, well, it diverges. Meaning we don't get a number when we calculate the integral. So we say it diverges. How does this help us determine what the series does? Well, notice this pattern of the rectangle sticking out above the area under the curve is going to be consistent throughout. So if this yellow area extending it forever is going to equal infinity in the limit, then that means the series is also going to have that same property. Because the series is more than that. It's sticking out above it. Now, quick warning. The picture here will not always involve the series sticking out above. We're doing this for our convenience. Ahead of time, I predicted that this integral would diverge. So when I was drawing these rectangles, I did it in such a way where this extra stuff was going to be sticking out above the area here. Because what's greater than infinity? Infinity. So that tells me this series will have to diverge.